functions, we're actually going to consider it like a transformation. So given a function f of x, we are going to take the square root of that function, graph it, find important properties like domain and range, invariant points, etc. Okay? So absolute value we touched on, reciprocal we touched on, and so last year, so now square root of a function. So complete the table of values for the function y equals x minus 2. We already graphed some of these and solved graphically last week, but now we're going to look at it in terms of it actually like a transformation where we already have our x minus y equals x minus 2, and then we take the square root. Okay? So you can fill in the chart here, x minus 2. So when x is 0, you get negative 2, negative 1, 0, 0.3, 0.6, 1, 2, 3. Okay. Now what happens when you take the square root? So this is now your radicand. So we're looking really at taking the square root of the second column here. Well, can you take the square root of negative 2? No. Negative 1? No. We're dealing with a real number system. You can't. Square root of 0 is 0. Square root of root 3. .55. I'll just go to a couple of decimal places. 0.6 square root. 0.77. Square root of 1 is 1. Square root of 2 is, we're going to use this a little bit more in trig 1.41. Square root of 3, 1.7. Square root of 3, 1.73. Square root of 4 is 2. Okay, so let's graph. It says, graph both of them. So I'll do the original in blue. Oh, that's not the one. Okay, so slope blue is 1. So make sure you take a look at the scale or the grid markings, what they represent. Okay, so now we'll do the square root of x minus 2. Based on our work from last week, you know the vertex should be at 2, 0, right? If we're thinking about this transformation, there aren't going to be any points for x less than 2. Because these points here all have a y value that's negative, and you can't take the root of it. So that's why our first point here is 2, 0. And then 2.3 is about what? There. And it is 0.55, so maybe about like that. 2.6 is 0.77, so about like that. 3 is 1. 4 is 1.41. 5 is 1.7. 6 is 2. horizontal parabola, just like we learned before. But when you consider it based on the transformation of the graph y equals x minus 2, you just have to be a little bit careful about this part here. Okay? Sometimes we might give you a graph, no equation for it. It might not even be a line, right? You might not know how to come up with the equation of it. But you need to be careful when you're taking the square root of it. The fact that students forget is when you take a square root of a number that's less than 1, you actually get a bigger number than what you started with, right? So here, when we took the square root of 0.3, we got a bigger number than what we started with.
Because it's 0.5 times 0.5.
You have to square this back, right? So when you're dealing with a decimal less than 1 and square that, you end up with a smaller number.
Multiply by less than 1, it gets smaller.
Right? 1/2 squared is 1/4. It's smaller. So when you think about it, working backwards, it helps. So this number, when I square root it, it's bigger than what you have. Anything greater than 1, when you square root it, you get something smaller. Okay? So this part here, for every x value, okay, your y value is going to be bigger than what it was originally. Anything, for any point where the y is greater than 1, it's going to be smaller. Okay, so just remember that if you're asked to sketch something. Because sometimes students are really lazy and they will just like kind of put it right on top of that line and you're going to get marks taken off her if we ask you to sketch that.
You have to show like there's a gap.
Yeah, show that there's a gap, exactly. Okay, so where does the square root of x minus 2 exist? Where the y coordinates of y equals x minus 2 are greater than or equal to 1. Since it's in words, I'll write it in words. Okay, so there's some invariant points.
Greater than or equal to 0.
Oh. Greater than or equal to 0. No, we're talking about the y. Yeah, y coordinates. Greater than or equal to 0. Sorry. Because it's the y coordinates of this. So as long as the y coordinates of this are greater than or equal to 0, then you can take the square root. Sorry about that. Just thinking the greater than. Okay, so the invariant points occur. There's 2 of them. So this one here and this one here. Okay, so y coordinates at that one are 0, y coordinates there 1. So in this case, the invariant points are coordinates 2, 0 and 3, 1. So we just talked about this. Between the invariant points, the graph of y equals root of x minus 2 was above. Okay, so the square root of x minus 2 was above the original graph. While for the remainder, the square root function was below. Okay, so question 2, the original and the square root function are shown. So you can see it's very obvious there. Sometimes you have to almost accentuate it if your grid is really small and it's hard to see. In any case, you can see it there. The original is a parabola, okay? Notice how the vertex is below the x-axis and it's opening up. So our transform function, our square root function, is split into two arms, right? There is nothing between those 2 points because you cannot take the root of a negative. So sometimes that happens. It depends what your original function is. So the domain of the original here for any parabola is all real numbers. Okay, but for the radical function, it's x less than or equal to -3, or x greater than or equal to 1, because those are the x-intercepts of that original graph, and everything in between there is below the x-axis.
Do you use the union symbol when you're doing set or the
When you use interval notation. So if you use interval, you would go -infinity to -3, union 1 to positive infinity.
Definitely not the, what is the other one called?
Intersection.
Yeah, definitely not the intersection.
Okay, so the square root function exists only where the radicand f of x is greater than or equal to 0. The range of the original, that's going to be greater than or equal to -4. Okay, of the radical, remember, smallest value here is 0. So the smallest could be 0. Now, does that mean that it is always going to be greater than or equal to 0? No. Depends what's here. Maybe you have a parabola that has a vertex up high there and it opens up, right? When you take the square root, it's not necessarily going to go back down to 0, right? No, it's not going to. So you do have to know what your original is. In this case, if it does cross the x-axis and opens up, it's going to be greater than 0. Greater than or equal to. But that will depend on what your original function is. Because if you have something like this, so you have that, and you have to take the square root of that function. So your y value is 4, square root is 2. This would be square root of 5, so this is going to be always, these are all positive, right? And so it's going to look something like that, and it's never going to go to 0, right? It's going to be still have 1 x 5 2.
So it's like a parabola, but like at the vertex, you flip the arms.
Just like this right there, right? Okay, so the invariant points occur when the y coordinates are 0 or 1. Invariant points rounded to the nearest tenth where necessary are approximately. So we're just going to approximate them. Well, these ones are approximate. We can get those exactly, right? So -3, 0. And 1, 0. Then here, okay, so that's 1.5. I'd say 1.25. It says nearest 10. 1.3. And then this will be the same the other way, -3.3. Okay, those are approximate. We're estimating from the graph. We're going to get the exact values in a little bit. Okay, so just to summarize here, square root function exists only where f of x is greater than or equal to 0. That is where the graph of f of x lies on or above the x-axis. Domain. Consists only of the values of the domain of f of x for which f of x is greater than 0. Invariant points when it equals 0 or 1. Okay, so now it's split up into parts here. Okay, so if your radicand, your f of x, has a value that's less than 0, means it's negative. If you're trying to take the square root of it, you can't. So the graph of the square root of f of x, where f of x is less than 0, does not exist. Okay. Then, if you have f of x equaling 0, taking the square root of it, you get 0. This you get 0. So they're intersecting on what axis? The x-axis, exactly. Okay, and that will give you invariant points. Okay. Now, if that f of x value, so your y value is between 0 and 1, remember, when you take the root of it, the graph that you plot is going to be above the original graph. Okay. If the radicand is equal to 1, then the graphs of these will intersect. Okay, and give you invariant points as well. And then if f of x is greater than 1, that means this value will be bigger than 1, and remember, that means your square root function will be below the original. Okay, so that's kind of a summary chart. So let's practice. I'm just going to minimize this a little bit. Okay. So linear function here. I always start with plotting the invariant points. So first of all, nothing's going to happen for the x values over here because that's negative. I'm going to plot that invariant point, plot that invariant point. So you've got 2. Then, just like the last one, you can find more points. Think of nice y values. Okay, by nice I mean perfect squares, because you can take the square root. So the square root of 4 is 2. So for that same x value, just go down and plot for y value is 2. Same with 9. Go across and square root is 3. Okay, so we've got a few points. Now you need to be really careful. I'm going to actually make this a little bit thinner. Okay, so from here, I'm going to go above, and then it's below. Well, I could have it above, but a little hard to see this. So what you're doing, make it a little more obvious. There. Okay? Because the square root of a number between 0 and 1 is larger than the original number you take the square root of. Okay? Okay, next one is a parabola that opens down. So this one's a little bit different. It's going to be continuous between -2 and 4, but that is going to end. No arrows, because I cannot take the root of these points, right? The y value is there. So always got your invariant points. Okay. Then choose some other nice points. So vertex is important to do. It's not actually that nice, but it's important to do. 4 obviously is nice. Square root of 4 is 2. Look across to where it's 4 again. That's 2. And then I would estimate this. That's what, about 4.5? So when you take the square root, 4.5, you get 2.12. So 2.12, kind of about there. And again, try to make it obvious that these are above. So, and use pencil, because sometimes you'll have to try it again. Third. Not for it's a little, it's a little bit better. It's a little bit. So at least you can see. So do not put arrows on the end. If you put arrows there, you get marks taken off. Right? And
So weirdo looking graph.
Okay. Okay, next one is a parabola that opens up. It doesn't cross the x-axis, so we can take the root of the whole thing. Okay, so in this case, the domain will be all real numbers. There's only one invariant point. Does not cross the x-axis, right? So there's no invariant points when y is 0. Okay, so that's going to be on our new point, new graph. I'm going to start with the perfect square. So 4 square root of is 2. So for that same x value, sometimes students know that square root of 4 is 2. You should know that it's 2, but then they don't know where to put the point. It's for that particular x value that the y value is 4. So it's going to be the same x value on your new graph. Same thing here. Okay, and then 9 is 3. Okay, and then if you're not sure in here, so what was the square root of 2? Is 1.41 approximately. Same on the other side. Okay, so it's actually something like that. Almost making it linear, right? If you think about x squared and then square rooting that, almost linear. What do we do with the D?
Dot.
1 dot.
How would you like write the equation for that? Would
You
you
could
just
say the equation for it.
it's just
Around
The
just 0
square root, well, that's the square root of 0. It's just 1 equals 0 at that point. So
0 equals 0.
yeah, so the domain is x equals -2. That's it.
Wow. So the entire equation could just be like the set, and then like, nice.
Well, you would just put domain is that, right?
Yeah.
Okay. So algebraically determine the domain of each function. So based on what we already kind of did this back when we were in the first day, right, finding the domain and range of some of those radical functions. This is just maybe thinking about more about the radicand being the original function. Kind of up to you, but we know, that we need negative 3x plus 12 to be greater than or equal to 0. Okay, so you're just doing that work. If you're solving that inequality just like that, then remember, if you're dividing or multiplying an inequality by a negative, it changes the direction of the inequality sign. If you want to use transformations like we did in the first day, right, that kind of, you can factor out the negative 3 and see that x has to be compared to 4 because of that reflection over the y-axis. It's going to be less than or equal to 4. So however you want to do it, right? We're not really going to compare as long as there's some kind of work. Doing this, doing that tells me, and then just putting it into your domain notation. Next one requires you to think a little bit back to math 20, right? Because we want 3x squared minus 14x minus 5 to be greater than or equal to 0. Well, that is a quadratic. So, easiest if you can factor, Victor? No. Okay. If you can factor, otherwise you'll have to use quadratic formula. Okay. You can't factor that, so do that. Okay, so then you have to think about how to solve that algebraically. It says algebraically. So we factored it. Back in Math 20, you learned that you could do case analysis, look at the factors. If that has to be greater than or equal to 0, then both the factors have to be positive or both negative, right? You could do a chart if you wanted to. You could do a number line. I tend to do that. So here, so here, negative 1/3 and positive 5. You could do a sketch if you want. This is opened up, so this would look like this. Okay, and we want it to be positive, so then we're looking for this and this. Okay, or this is what's positive, right? Or you could use test values, right, on here. Say, let's test x equals -1. Okay, that would give me a negative times a negative, which is a positive. X equals 0 gives me a negative. X equals 6, something like that. So test cases or that chart. Okay, somehow you have to show that you know your solutions here. So now your domain is x
You can't just, if it says algebraically determined, you can't just graph it on your calculator and state it. Okay, somehow you have to show some work for that. Okay, algebraically determine the exact value. Exact value means fractions in most terms, square roots, simplified, no decimals. Maybe we might accept if it was terminating decimal, but try not to.
If you have, let's say, like a, what's it called? Non-irrational denominator, would you consider that exact value?
Irrational denominator is exact, but it's not simplified.
What if it's like a cube root?
It's exact, but not simplified.
Not that.
You still, to be simplified, you can't have radicals in the denominator, whatever root it is.
Okay. Why is that? That doesn't make any sense. Nomenclature?
Yeah, just to be
Math.
proper form. Yeah. Okay, so invariant points when x equals 0, when y equals 0, so in this case when f of x equals 0, you'll get invariant points, and when f of x equals 1. Okay? So 0 equals x squared minus 2x minus 8. See if you can factor. If you can't factor, you're going to have to use the quadratic formula. It says exact. That one you can factor. Okay, you don't just leave it. It says the coordinates. Those are not coordinates. And you need to make sure you put the correct y coordinate. So this is for invariant points when y is 0. So that's going to be negative 2, 0, and 4, 0. Okay, and then same when y is 1. So in this case, got to bring the 1 over. And that one you're going to have to use the quadratic formula. Hopefully you've got this memorized.
And if you ever forget, you can always just drag it. Well, that takes so much time.
Yeah, Jackson.
No, seriously.
I know.
Actually, what I usually do is if the coefficient on the highest degree term is 1, then I'll just complete the square.
Oh, yeah.
Yeah.
And you can complete the square. Okay? Don't just do this. Some of you are so lazy in your work. Okay? That means nothing like that. Just some number. Right? What are we doing this for? We're trying to find the value of x. Okay? So don't be lazy. Same thing here. If you bring the 1 over, don't drop that. That's 0 equals. If you just leave it as x squared minus 2x minus 9, it's just an expression. Right? It's just representing some number depending on what x is. It's not an equation. Even nicer if you write x equals all the way down. Okay, I'm not done. Coordinates, good, Victor. You got it. I'll put it over here. So 1 plus root 10, and that was when y was 1. 1 minus root 10, when y is 1. Okay? Calculator. Second. What do y equals? Okay. What's our original? So x squared minus 2x minus 8. Oh, that's okay. Didn't remember what that. So I had a standard screen there. Yeah, you could graph the square root, but why bother? Can you put your phones down so it's not quite as obvious that you're ignoring me? So, y2 equals 1. I mean, that one's pretty obvious. I would just do y equals 1. I wouldn't do the square root of the function because this is way faster. Second trace intersect. Enter, enter, enter. Copy out the x value. That's the leftmost x value. Okay, folks? That's the leftmost one, so that would be for 1 minus root 10. Oh, sorry.
Oh, is that the analog button?
There you go.
Okay, and I got the same thing. So it's going to be correct. Can you guys stop holding masks like COVID, first of all? Seriously.
We love you, Miss Smith.
Okay, so that is the end of that one.